Study Unit 7, Lecture 1. Study Unit 7 focuses on DC to AC converters. The first half of the study unit, so the first 3 lectures, will focus on switched mode converters, and the second half of the study unit will focus on resonant mode converters. So these converters are also sometimes referred to as inverters, where inversion is the conversion of DC power to some type of AC power at some desired output and current frequency. So in general there are 2 types. There is a voltage source inverter and a current source inverter. The key distinction between the two is that a voltage source inverter will generate a constant voltage at the output with varying current, whereas a current source inverter will provide a constant current with the output voltage changing depending on what the load requirement is. A secondary distinction is that a voltage source inverter is able to handle an open circuit at the output, and a current source inverter is able to handle a short circuit. A good way to evaluate the quality of the output of the inverter is to look at the quality of the output signal in terms of the harmonic distortion which is present. In other words, the purer the sinusoid at the output of the DC to AC inverter, the fewer harmonics it will have. So harmonics can be characterized by rho n, which is the absolute value of Vn, which is the voltage at a particular harmonic, divided by the fundamental, and this can be expressed as n mu n, where n must be larger than 1. Mu n is referred to as the distortion factor in the harmonic expression. Finally, the total harmonic distortion is given by this equation over here. So your THD will be equal to the square root of the sum from n to equal to 2 to infinity of rho n over n squared. Simply put, the less total harmonic distortion there is, the purer the sinusoidal output of the inverter. Shown here is a single phase bridge inverter. Here are the 2 parts of the bridge, and this is the load in the center. The DC voltage is applied across the bridge, and depending on the state of the various thyristors which are present in the bridge, a AC current will be stimulated through the load. So in this example, the switches are implemented with thyristors, but they could be implemented with mechanical switches or some other solid state device such as a MOSFET or gated BJT. The diodes which are present in each leg of the bridge are not necessarily needed, but if there is some inductive property in the load, then these diodes act as freewheeling diodes, so any energy that remains in the load is allowed to pass through the diode during a switching transition. So this bridge circuit can operate in 2 modes. There is a mode where it produces square wave output, and there is a mode where it produces a stepped square wave output. So the square wave or bipolar output is going to be the first type of AC signal that will be considered. So in this first bipolar configuration, each branch or each leg of the bridge switches at 180 degrees out of phase. So the first 180 degrees of the cycle, one leg will be on, and for the remainder of the cycle, the other leg will be on. When the bridge is operated in this way, then the current which flows through the load can be described by this equation. Simply the supply voltage is equal to the voltage across the inductor plus the voltage over the resistive component of the load, and the inductor voltage, as always, is expressed as the IDT because the inductor current is changing. Because the circuit operates in 2 modes, one with a supply voltage that's high and another where the supply voltage across the load is inverted, there will be 2 expressions for the current depending on which part of the AC signal is under consideration. So this expression here is for the first part over here, where the supply voltage is positive. When the output voltage is inverted, then the current through the load is given by this expression over here. The expression for the voltage across the load is the same as for the case when the output supply voltage was positive, except now the output voltage has been inverted. So this expression is valid from time t0 to t1, and then this expression is valid from time t1 to t2. Assuming an initial current of 0, then this differential equation can be solved for I, and this gives a load current given by Vs over R multiplied by 1 minus e to the minus t over tau, where tau is the time constant of the inductive and resistive load and is equal to L over R. So expanding on this idea, Once the circuit is in steady state, then there will be two expressions which describe the current depending on which part of the bipolar cycle the current is flowing. So in the first part, the current is given by, well, the current as a function of time is Vs of R minus Vs of R minus I min multiplied by e to the minus t over tau, where this I min is the initial current at the beginning of the cycle over here. For the period where the output is negative, or the second part of the bipolar cycle, the current is given by IL equals Vs over R plus Vs over R plus I max multiplied by e to the minus t over tau, where I max is the boundary condition at the end of the cycle where the output current has reached some other maximum. In the circuit in steady state, the current during the start of the positive phase will equal the current at the or the inverse of the current at the start of the negative phase. And this way, I min and I max can be solved for. Equating these two expressions at the boundary conditions allows for I min and I max to be solved for, and the answer to that is at the boundary conditions the current is given by Vs over R multiplied by the hyperbolic tan of T1 over 2 tau. It is also possible to determine at which point the current polarity will go from negative to positive when it passes through some time Tx. So at time Tx the current is 0, so the 0 current plugged into here, and Tx can be solved for. So this crossing point where the current crosses through the axis and changes polarity is given by tau multiplied by the ln of 1 plus either I max or I min multiplied by R divided by Vs, depending on whether the minimum or maximum boundary condition value for the current is used. The sign will also change. So now that the currents through the load have been defined, it is possible to define the currents which are experienced by the switches or the thyristors in this case. So at this node here, node A, there are three different currents. There is the current flowing through the load, there is the current flowing through the thyristors, and there is the current flowing through the diodes. The same is true at node B. There's a load current, a thyristor current, and a diode current. So the average thyristor and diode current can be determined by taking the integral over the applicable time period of the current which is flowing to that particular device. So for example, when the current is positive, the current will be flowing from the source through T1, through the load, down through T2, and then back to the negative supply. So in this case, that is the average current from Tx, where the current is larger than 0, to T1. For examples here, where the diode, or rather where the current is being reversed, then the freewheeling diodes will allow the current from the load to flow back towards the source. So this means that the average diode current is given by 1 over T2 multiplied by the average current, which is integral from 0 to Tx, and this is where the current is negative, of the inductor current. So what's happening here, say that T1 is turned on, so the current flowing through T1, through the load, and then through T2. But when these are switched off, there is a negative current, and there's some reactive component in the load, and this current will continue to flow through these diodes over here, D3 and D4, to get back towards the load. The average supply current can be then calculated using these equations, and is simply twice the average thyristor current minus the diode current. Finally, the sort of idealized power usage will be equal to P equals 1 over T1 multiplied by the average supply voltage multiplied by the current from 0 to T1, and this is simply supply voltage multiplied by the average supply current. So at the beginning of the lecture it was mentioned that the total harmonic distortion measurement or calculation can be used to determine the quality of the converter, and this will also be done for all the converters which are examined in the study unit. So for this circuit, the instantaneous load voltage is given by this expression over here. It is 4 pi multiplied by supply voltage multiplied by the summation of n odd to infinity of 1 over n multiplied by of sine n omega 0 t. This expression here is from writing the Fourier expansion for the instantaneous output voltage. So looking at the fundamental component of the AC signal at the output, so this is when n equals 1, then the output voltage simply reduces to 2 multiplied by root 2 divided by pi multiplied by the supply voltage, which equals 0.9 multiplied by the supply voltage. What this means is that 90% of the energy is contained in the fundamental at the output. The load current can also be defined in a similar Fourier expansion, as well as the power, and that's a good exercise for a student to have a look and read through the reference text to see how these quantities, or rather how these expressions, are derived. An alternative to the bipolar mode is the quasi-square wave output mode. In this mode, an attempt is made to more closely simulate a AC signal in the output voltage by having an additional step in the output square wave. The idea being here, by more closely simulating the desired output AC signal, it is possible to reduce the total harmonic distortion at the output, and thus have more power delivered in the fundamental. Another way of stating this is that the output RMS voltage can be varied by manipulating the shape of the square wave and introducing zeros into the square wave. So to compare this to the bipolar case, in the bipolar case, for example, thyristor T1 and T2 would be on simultaneously, and T3 and T4 would be on simultaneously. But for the quasi-square wave case, there is a phase difference in the switching cycle between the different thyristors. In other words, the thyristors are not all switched simultaneously. So for example here, in the first part of the cycle, T1 and T2 are on as in the bipolar case. But in the second part, or before the second part of the cycle, there's a phase where only T1 is on and the other thyristors are off, and D3 comes into play to conduct current back to the source. This can then be expanded to get a dead zone by only allowing D3 and D4 to conduct, and finally to get the lower part of the square wave, T3 and T4 conduct, and finally by repeating what was done initially, the upward step of the quasi-square wave can be generated. So during these zeros, the output current or output voltage is equal to 0, and that allows us to write this expression where the supply voltage is 0 equals to the load inductor voltage plus the resistive voltage. A term often used to describe the case where the voltage across the inductor and the resistive load are 0 is when a 0 voltage loop forms in the circuit. So for example over here, in this 0 case over here, conduction is only through T1, through the load, and then D3. This means that the 0 voltage loop is formed in this conductive path over here. It should be noted that there are multiple 0 voltage loops in this circuit, so there is not necessarily a reliance on this T1 D3 loop to generate the 0 voltage, but there's also a T3 D1 loop. Yeah, there we go. T3 D1 loop, which will also generate a 0 voltage. And these 0 voltage loops will be alternated throughout the cycle, and this is to reduce stresses on the actual semiconductors. So as with the bipolar case, currents can be defined for the quasi-single phase bridge inverter or single phase output by defining currents for each of the three possible voltage outputs. So there are three cases. There's a case when the output voltage is larger than 0, equal to 0, and less than 0. So there will be three different currents which need to be defined. For the case where the output voltage is larger than 0, then the output current is less than 0, and the expression for the output current is simply Vs of R minus Vs of R minus I out multiplied by e to the minus t over tau. When the output is negative, the current can be expressed as minus Vs of R plus Vs of R plus Vi multiplied by minus t over tau. In other words, it is simply the polarity reversed version of the current during the first part of the cycle. When the output voltage is 0, the output current is simply equal to Imax multiplied by e to the minus t over tau, where Imax is the maximum possible voltage in the cycle. So once again, a Fourier expression can be derived to express the instantaneous output voltage across the load, and for the quasi-square wave output, it is simply 4 over pi multiplied by the supply voltage multiplied by the sum of n r to infinity of cos n alpha over 2 over n multiplied by sine n omega 0 t. For the fundamental, this whole thing simplifies to 0.9 Vs multiplied by cos alpha over 2. This angle alpha is no different to the AC to DC converters. It is effectively a delay angle from the end of the first cycle to when the second cycle starts, and it is just during this delay period that the output voltage is 0. So there is no reason why these pulses which are generated by turning the thyristors on and off, you need to follow a regular pattern as shown here. These pulses can be modulated to control the RMS voltage at the output. So there are two pulse width modulation techniques which can be used to vary these pulse widths. There is the bipolar pulse width modulation and there is a multi-level pulse width modulation. So how these control schemes work, there will be some sawtooth wave as well as a reference sinusoid which represents the desired output. The sinusoid will be modulated onto the sawtooth, and wherever there is an intersection of the sawtooth and the sine wave, it will trigger the switches to switch, and in this way we're able to modulate the rate as well as the width of the switches. So for the bipolar case over here, this pulse stream over here will allow for the simple bipolar switching scheme to more closely approximate the desired reference sine wave output. For the quasi-square wave bridge, it is possible to perform the same type of modulation function by making use of two sawtooth waves which are 180 degrees out of phase. The one sawtooth wave will be compared to the reference frequency to generate one set of switching signals for one leg of the bridge, and the 180 degrees out of phase sawtooth will be used to generate the switching characteristics for the second leg of the bridge. So back to the unipolar. The unipolar produces a single unipolar output which is used to control the bridge, but for the multi-level, the sum of the two reference signals can be used to generate the control signal output for a multi-level quasi-square wave bridge. So the key difference between these two different methods is the harmonic content of the output signal. So for the bipolar method, there is a strong fundamental with regular harmonics. With the multi-level PWM method, there is no fundamental and the remaining harmonics are actually quite weak. Also note that there is no third harmonic. The absence of the third harmonic means that there are no triple N harmonics, so there won't be a 6th, a 9th, a 12th, 15th and so on harmonic either. What this means that in general, the total harmonic distortion when using multi-level PWM will be much lower than for the bipolar case, and the purity of the output sinusoid from the DC to AC converter will be much better. And that concludes this lecture.